This video explores the topic of accelerometers within the framework of the European project titled Personalized Education in Measurement Science and Technology Empowered by Machine Learning. The aim of this tutorial is to introduce the basic types, operating principles, key characteristics, and applications of accelerometers. Accelerometers are sensors used to measure acceleration. A system with no acceleration, either at rest or moving at constant velocity, is called an inertial system, while a system with acceleration is a non-inertial system. In non-inertial systems, an inertial force acts on all bodies with mass, according to Newton's second law. For example, a bus standing at a stop is an inertial system. When it starts moving and accelerates, it becomes a non-inertial system, and passengers feel an inertial force pushing them backward. When the bus brakes, the inertial force pulls passengers forward. During a turn, passengers also experience an inertial force because circular motion involves acceleration due to a change in the velocity vector. Therefore, whenever a mass is placed in an accelerating system, an inertial force acts on it. This principle is fundamental to the operation of accelerometers. An accelerometer consists of an inertial mass coupled to a sensitive element, such as a piezoelectric crystal or a capacitive structure. When the system accelerates, the inertial force causes the mass to press on the sensitive element, which generates an output signal. In piezoelectric sensors, this signal is an electric charge, while in capacitive sensors, it is a change in capacitance. Since the force is proportional to acceleration, the output signal is also proportional to acceleration. The sensitivity of an accelerometer depends on the inertial mass. A larger mass produces a greater force for the same acceleration, resulting in a higher output signal and greater sensitivity. The main types of accelerometers are piezoelectric, capacitive, and MEMS accelerometers. The basic components of a piezoelectric accelerometer are a piezoelectric crystal and an inertial mass. When acceleration occurs along the sensitive axis of the accelerometer, an inertial force, proportional to the acceleration, acts on the inertial mass, causing it to press against the piezoelectric crystal, which generates an electric charge proportional to the applied acceleration. A capacitive accelerometer consists of an inertial mass attached to a movable capacitor electrode. When acceleration is applied, the resulting inertial force causes the mass, and thus the movable electrode, to displace, changing the distance between the electrodes and, consequently, the capacitance. This capacitance variation is processed by an electrical circuit, such as a bridge or an oscillator, to generate an output voltage or frequency proportional to the applied acceleration. MEMS accelerometers are accelerometers manufactured using MEMS technology, where MEMS stands for Micro-Electromechanical Systems. First, we consider piezoelectric accelerometers. The piezoelectric effect is the ability of certain materials to generate an electric charge when mechanical stress is applied. Piezoelectric materials can be classified into natural and synthetic types. Natural materials include quartz, tourmaline, topaz, and Rochelle salt, while synthetic materials are mainly piezoelectric ceramics, most notably PZT ceramics, which are the most widely used. The piezoelectric effect can be explained using a simple molecular model. Without an external force, the centers of positive and negative charges coincide, so no piezoelectric effect occurs. When a force is applied, the molecule deforms, separating the charges and forming an electric dipole. In a bulk material, internal charges cancel, but uncompensated charges appear at the ends of the material. These charges are collected using metal electrodes. The piezoelectric effect originates from the crystal lattice structure and occurs only in non-centrosymmetric crystals. In quartz, an external force deforms the crystal unit cell, causing positive charges, silicon ions, to accumulate on one side and negative charges, oxygen ions, on the other. In PZT ceramics, the total charge of each unit cell is initially zero, but a slight displacement of the titanium ion makes the unit cell behave as an electric dipole. When a mechanical force is applied, this displacement increases, leading to higher polarization. Each piezoelectric material has a maximum operating temperature, called the Curie temperature, above which it loses its piezoelectric properties. Natural piezoelectric materials are monocrystalline, while synthetic piezoelectric ceramics are polycrystalline, and consist of domains with differently oriented dipoles that partially cancel each other. To obtain a strong piezoelectric effect, these dipoles must be aligned in the same direction through a process called poling, which is performed by applying a strong electric field at elevated temperature. During poling, the dipoles align with the applied field and retain this orientation after the field is removed. PZT ceramics are the dominant material in piezoelectric accelerometers because of their very high sensitivity, which is much greater than that of quartz. For the same applied force, PZT generates significantly more electric charge. Since vibration-related forces are usually very small, especially at low frequencies, high sensitivity is essential. This allows PZT-based accelerometers to measure vibrations even below 1 Hz. In addition, PZT has a higher resonant frequency than quartz, providing a wider bandwidth and enabling accurate high-frequency vibration measurements. Quartz, on the other hand, offers excellent temperature stability and shows virtually no aging, making it highly stable over long periods. However, due to its low sensitivity, quartz is less suitable for vibration measurements and is mainly used where high sensitivity is not required. An important advantage of PZT is its manufacturing flexibility. While quartz has fixed piezoelectric directions determined by its crystal structure, PZT ceramics gain piezoelectric properties during the poling process, allowing them to be freely shaped before polarization. A piezoelectric accelerometer can be modeled as a second-order mass spring system with negligible damping. Such a system has a natural resonant frequency at which the frequency response shows a strong peak, as given by the expression on the slide. The useful frequency range is defined as the range in which the accelerometer sensitivity remains essentially constant. In practice, the upper frequency limit is usually taken as 1/3 of the resonant frequency. Small, low-mass accelerometers can have very high resonant frequencies, up to about 180 kHz, but they offer lower sensitivity. In contrast, more sensitive general-purpose accelerometers typically have a resonant frequency around 30 kHz, which corresponds to an upper usable frequency of about 10 kHz. The two main types of piezoelectric accelerometers are compression and shear, classified by how the inertial mass applies force to the piezoelectric crystal along a specific crystallographic axis. In shear accelerometers, a shearing force is applied to the crystal. The crystals are clamped between a central post and the inertial mass, and the assembly is fixed with a screw or clamping ring. The most common shear designs are delta and planar. Compression accelerometers have a simpler structure. The piezoelectric crystal is placed between a flat base and the inertial mass and is typically held together by a single central screw. If all other parameters are the same, compression-type accelerometers have stiffer crystals and therefore a higher natural resonant frequency, giving a slightly wider frequency range. Shear-type accelerometers, however, generate about 40% higher output voltage for the same applied force, which allows the use of a smaller inertial mass. These differences result from different crystal cutting orientations. Piezoelectric crystals generate voltage under vibration-induced pressure, but unwanted pressures cause noise and measurement errors. Compression-type accelerometers are more sensitive to base bending and thermal transients, which can produce large errors in environments with mechanical deformation or rapid temperature changes. In shear accelerometers, the supporting post is mechanically isolated from bending and thermal stresses, making them far less sensitive to these effects and more accurate. Although shear accelerometers are more complex to manufacture, modern production methods make them cost-effective. While early piezoelectric accelerometers were mainly compression type, most modern devices are shear type due to their higher sensitivity and better performance in demanding industrial conditions. Charge amplifiers are commonly used to amplify the output of piezoelectric accelerometers. A charge amplifier is essentially an operational amplifier with a feedback capacitor in the negative feedback loop. In practice, the piezoelectric accelerometer is connected to the amplifier by a cable. The cable capacitance can be problematic because it depends on cable length, which would otherwise cause the system sensitivity to vary. However, due to the virtual ground at the input of the charge amplifier, the effects of parasitic resistances and capacitances, including cable capacitance, are effectively canceled and do not influence the output voltage. The operating principle of the charge amplifier is as follows. The piezoelectric crystal generates a time-varying charge, which produces a current that flows entirely into the feedback capacitor. As a result, the generated charge is fully transferred to this capacitor. The output voltage is therefore directly proportional to the generated charge, which is why the circuit is called a charge amplifier. A charge amplifier has the following advantages. It provides an output voltage linearly proportional to the generated charge, eliminates the influence of parasitic capacitances and resistances, including cable capacitance, and offers extremely high input impedance, which is essential for proper matching with the high output impedance of piezoelectric accelerometers. Accelerometers can operate in charge mode or voltage mode. In charge mode, the output is an electric charge. This charge is transmitted through a cable to a charge amplifier, which converts it into a voltage and transforms the high output impedance into a low one, enabling further signal processing. Because of the high output impedance of the accelerometer, special low-noise cables are required, which increases cost and complicates system setup. In voltage mode, also known as IEPE or ICP, the accelerometer includes a built-in amplifier that converts charge to voltage and lowers the output impedance. The sensor directly provides a low-impedance voltage signal to the data acquisition system, eliminating the need for a charge amplifier and special cables. This simplifies installation and reduces cost. IEPE accelerometers require power, typically supplied through a 2-wire cable, with one wire carrying both power and signal and the other serving as ground. Their operating temperature is usually limited to about 120 degrees Celsius due to the integrated electronics, whereas charge mode accelerometers can operate reliably at much higher temperatures. Now let's consider the influence of mounting techniques for piezoelectric accelerometers. For accurate measurements, the accelerometer must be mounted by achieving the strongest possible connection between the accelerometer and the object, to ensure vibrations from the object are efficiently transmitted to the sensor, especially at high frequencies. It should be mounted only on a flat, clean surface. Before installation, the surface must be carefully cleaned, usually with compressed air, to remove metal particles, oil, and other contaminants. A thin layer of silicone grease is applied to fill gaps from surface imperfections. As previously mentioned, an ideally mounted accelerometer behaves like a single mass spring system with a natural resonant frequency, as illustrated in the first figure. However, non-ideal mounting caused by uneven surfaces, residual particles, or magnetic and adhesive mounts acts as an additional mass spring system, creating a second resonant frequency, as shown in the second figure. This narrows the frequency range over which the response remains flat. In conclusion, a poorly mounted accelerometer has a significantly smaller usable frequency bandwidth compared to a well-mounted one. The way an accelerometer is mounted directly affects its frequency bandwidth. Screwing it onto a clean, flat surface with a high-quality finish gives the widest frequency range and the most secure connection, while adhesive glue or magnetic mounting can significantly reduce the frequency bandwidth. However, screwing requires drilling a hole in the surface of the object where the accelerometer is to be mounted, which can be impractical, such as on very thin metal sheets. In these cases, adhesive or magnetic mounting is used. For adhesive mounting, the adhesive layer should be as thin as possible, since thicker layers reduce the frequency range. Cyanoacrylate adhesives are ideal because they bond strongly even in thin layers and are removable with acetone. Often, the accelerometer is first screwed into an adhesive adapter, which is then glued to the surface. Magnetic mounting attaches the accelerometer to ferromagnetic surfaces, usually via a magnetic adapter. It allows easy installation, removal, and repositioning, but reduces the frequency range, typically suitable only for frequencies up to 2 kHz. The surface must be flat, clean, and free of oil, grease, debris, or thick paint. Now, let's look at MEMS accelerometers, a very current and widely used type of sensor. MEMS devices are extremely small, usually micrometers in size, and are made using microfabrication techniques adapted from microelectronics, such as photolithography, thin film deposition, ion implantation, and etching. In addition, MEMS-specific methods like bulk and surface micromachining are also used. Mass production techniques allow many MEMS devices to be made on a single substrate, keeping costs low. Unlike solid microelectronic devices, MEMS include cavities, cantilevers, membranes, and springs to perform mechanical functionalities. While silicon was initially the primary material used in MEMS fabrication, other materials like polymers, glass, quartz, and metals are now also common. MEMS fabrication differs from standard microelectronics with thicker layers, deeper etching, and processes for creating movable mechanical parts. Miniaturization is a key feature of MEMS. Small size and mass let MEMS sensors fit where conventional sensors cannot. MEMS sensors are cheaper and can be easily integrated with electronics such as amplifiers, memory, and communication modules, creating smart MEMS systems. Beyond small size and cost, MEMS allows new components and greater design flexibility. MEMS accelerometers have many applications. In the automotive industry, they are used for airbag systems. They are also found in military smart weapons, micro and nano satellites, mobile phones, digital cameras, and gaming controllers. Laptops use MEMS accelerometers to protect hard drives during falls. If a laptop is dropped, the accelerometer detects free fall and automatically powers down the hard drive to prevent damage. The two main types of MEMS accelerometers are capacitive and piezoresistive. Most MEMS accelerometers are implemented as capacitive sensors, offering high sensitivity and low temperature dependence. They use a comb-like structure, where a single movable structure, attached to the base via springs, acts as the inertial mass. This movable structure has multiple fingers, each of them placed between two fixed electrodes, forming two capacitors. Without acceleration, each finger is centered between the fixed electrodes. With acceleration, the inertial mass shifts by a displacement x, increasing the distance of each movable finger to one electrode by x and decreasing it to the other by x. As a result, one capacitance rises and the other falls. The capacitance change is proportional to the displacement x and thus to acceleration. To obtain a voltage proportional to acceleration, the MEMS capacitors from the previous slide are connected to the electrical circuit, as shown in the figure. The fixed plates are driven by rectangular pulses from an oscillator, with the upper and lower plates 180 degrees out of phase. The system acts as a capacitor voltage divider, whose output passes through a high impedance buffer to a demodulator. The output voltage, in the form of pulses, has an amplitude proportional to acceleration and a phase indicating its direction. Therefore, a phase-sensitive demodulator is needed. A two-dimensional capacitive MEMS accelerometer measures acceleration along two orthogonal axes, x and y, using a single movable inertial mass with comb fingers on all four sides. Fingers on the top and bottom sense x-axis acceleration, while left and right fingers sense y-axis acceleration. The outputs for each axis are separated in frequency by exciting their capacitors with AC voltages at different frequencies. A key challenge is cross-axis sensitivity. Acceleration along one axis can slightly affect the other axis's capacitors, causing undesired capacitance changes. Careful MEMS design is needed to minimize this and ensure accurate measurements. As the main advantage, capacitive MEMS accelerometers are largely temperature insensitive, so compensation is usually unnecessary, and they can operate reliably at elevated temperatures exceeding 125 Celsius degrees. With no mechanical contacts, they avoid friction and hysteresis, offering excellent stability, repeatability, and near-zero energy consumption. MEMS technology also allows close integration of signal processing circuits on the same substrate, reducing parasitic capacitance and improving measurement accuracy. The main limitation is high output impedance, which requires impedance matching circuits. Now we will consider piezoresistive MEMS accelerometers. The piezoresistive effect is the property of some materials to change their electrical resistance under mechanical stress, such as tension or compression. This is the principle behind strain gauges. In semiconductors, like silicon and germanium, discovered in 1954, the effect is much stronger than in metals, up to 100 times higher. Usually, doped P-type and N-type semiconductors are used. The effect depends on crystal orientation, dopant concentration, and temperature, with temperature being the main limitation. Piezoresistive MEMS accelerometers offer high output voltage and low impedance, ideal for direct signal processing. Their main drawback is high temperature sensitivity, requiring temperature compensation in wide temperature ranges. Now we will consider piezoresistive MEMS accelerometers. The piezoresistive effect is the property of some materials to change their electrical resistance under mechanical stress, such as tension or compression. This is the principle behind strain gauges. In semiconductors, like silicon and germanium, discovered in 1954, the effect is much stronger than in metals, up to 100 times higher. Usually, doped P-type and N-type semiconductors are used. The effect depends on crystal orientation, dopant concentration, and temperature, with temperature being the main limitation. Piezoresistive MEMS accelerometers offer high output voltage and low impedance, ideal for direct signal processing. Their main drawback is high temperature sensitivity, requiring temperature compensation in wide temperature ranges. These accelerometers consist of a beam with an inertial mass on top. Acceleration bends the beam, and a piezoresistor deposited on the beam changes resistance with deflection. This change is converted into an output voltage through an electrical circuit. Figures illustrate the principle and a typical device built this way. Vibration measurement is one of the key applications of accelerometers, primarily for the purpose of predictive maintenance. High-frequency vibrations, typically above 20 kHz, are important in predictive maintenance because they help detect early faults in mechanical systems. Vibrations are oscillatory motions around an equilibrium position and can be described by displacement, velocity, and acceleration. These quantities are related. Velocity is the derivative of displacement, and acceleration is the derivative of velocity. The amplitudes of these quantities are frequency-dependent. In the displacement spectrum, low-frequency components are dominant. In the velocity spectrum, mid-frequency components prevail, while in the acceleration spectrum, high-frequency components dominate. This means the choice of what to measure, displacement, velocity, or acceleration, depends on vibration frequency and sensor sensitivity. Traditionally, displacement was measured for very low frequencies up to 10 Hz, velocity for 10 Hz to 1 kHz, and acceleration for frequencies above 1 kHz. Today, wideband accelerometers cover very wide frequency ranges, from 0.5 Hz to over 20 kHz, allowing acceleration measurements even at low and medium frequencies. Displacement, velocity, and acceleration are interrelated. In theory, knowing one allows us to derive the other two through differentiation or integration. In practice, integration is much easier because differentiation amplifies noise. The figure illustrates this. Differentiating a noisy sinusoidal signal distorts it by increasing the noise, and double differentiation makes it nearly unusable. In contrast, integrating the same signal produces a clear sinusoid as noise tends to cancel out. Therefore, it is simpler to obtain velocity and displacement by integrating acceleration. Today, vibrations at all frequencies, low, medium, and high, are mostly measured using accelerometers. Wideband accelerometers make this possible, and since velocity and displacement can be derived from acceleration, measuring acceleration is fundamental for vibration analysis. Traditional piezoelectric accelerometers have been used for decades. Their technology is mature, offering accurate, reliable, and highly sensitive measurements across a wide frequency range, which makes them ideal for capturing high-frequency vibrations and predictive maintenance. MEMS accelerometers, on the other hand, are newer and rapidly evolving. They are low cost, up to 100 times cheaper than piezoelectric sensors, and compact. Their frequency range, typically several kilohertz, meets most predictive maintenance needs. While not yet matching piezoelectric performance, MEMS sensors are sufficient for most practical applications. One more key advantage of MEMS accelerometers is their easy integration with electronics and communication modules, enabling smart, compact, and cost-effective vibration sensing systems. As a result, they are increasingly adopted across many applications, including predictive maintenance. In this tutorial, we covered the essential concepts related to accelerometers. We began with the basic operating principle, which is based on Newton's second law of motion, and then introduced the main types of accelerometers: piezoelectric, capacitive, and MEMS. Next, we focused on piezoelectric accelerometers. We explained their operation based on the piezoelectric effect, the use of synthetic materials such as PZT ceramics for their fabrication, as well as their frequency response, which is linear from very low frequencies up to about 1/3 of the resonant frequency. We also discussed the main types, compression and shear, and emphasize the importance of proper mounting. In addition, we describe the role of charge amplifiers, which convert generated charge into a proportional voltage and minimize parasitic effects. We then introduced MEMS accelerometers, highlighting their small size, low-cost, IC-based fabrication and on-chip integration. Although they have a narrower frequency range than piezoelectric accelerometers, their performance continues to improve. The two main types of MEMS accelerometers, capacitive and piezoresistive, were also presented. Finally, we discussed the use of accelerometers in vibration measurement. These sensors dominate this field, enabling measurements from very low frequencies around 0.5 Hz to high frequencies above 20 kHz, and they play a key role in industrial predictive maintenance. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Niš and Politecnico di Milano, within the framework of the European project Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.